As you might get from the title, we're going to be talking about quantifying uncertainty in your models. So I'm going to talk about why this is important, kind of how to do this in the general sense, and then how to do it in the specific sense with a library I wrote to do it. Start off with a quick thank you to my employer, Capella Space, for sponsoring the talk. Standard disclaimer, I'm talking for myself and not for them. We can get started. So at the heart of all real rigorous decision making is the use of computational models. You try to capture how the world behaves and the state of the world, and feeding those states into your model, you get predictions, then you make decisions based on those predictions. Broadly, you get mechanistic models where you implement this with math and then a little bit of code. Or you have empirical models in the machine learning sense where you do this with math, a little bit of code, and magic. And I'm not a magician, so we're going to be talking about the first one, which has a lot of benefits going for it. You can open up the box and see what's inside, and there's a lot of advantages that go with it, but one of the inherent drawbacks is that the results here are too perfect. So we're looking at the Maxwell equations here for electricity and magnetism, and it gives you this nice magnetic field, and you're never going to see that in real life. The real world is noisy, it's messy, and if you try to make decisions based off of the predictions without taking into account the noise and the mess of the real world, you're going to be way off. So you really want to answer two questions here. Kind of what's the whole range of outcomes, and how sensitive are my predictions to the inputs? And so I have some kind of graphics on the next slides to really drive this home. So when you start off, this is something you probably do with any model you make. You have your input space, and you have your variables. So two variables here, and we say, this is my best estimate for variable 1, and this is my best estimate for variable 2, and I'm going to take that point, I'm going to run it through my model, and get my best point estimate. The problem with doing that is that in all this space out here, you have no idea what's going on. And unfortunately for you, in this case, that space is full of monsters. And it's kind of funny when these are 14th century woodblock prints, but it's less funny when you realize that this guy being held upside down by this sea creature represents your $1 billion rocket upside down flying towards the ground. So one thing you might try to do to capture this problem is vary all your inputs one at a time. You say, okay, this is the range of one of my variables, this is the range of one of my other variables. I'm going to look at these, try to capture its effects on the output. And that does pretty well, actually. This covers kind of half of the total area, optimistically. But you still run into the same problem that in the corners here, you still have monsters. And what's more, this doesn't scale very well. As you add more and more variables, the fraction of the total input space that you cover by just looking at each variable one at a time scales as 1 over that number factorial, which gets really, really bad really, really fast. And so the solution to this is random sampling. A Monte Carlo approach is kind of a term of art, and you might be familiar with it. I'm not going to prove it now, but you can show that as you add more and more points, the covered volume goes to the entirety of the input space. And what's more, you get better coverage within that volume. And what you end up is kind of much fuller exploration of the input space. And what that fuller exploration means is you actually understand the implications of what your model is saying. And so with that, we can answer the two questions we start off with. Kind of what is the range of possible outcomes, which kind of falls under this broad category of uncertainty analysis, and which parameters most affect these outcomes, which is kind of sensitivity analysis. And there's different tools that you can use to, and techniques you can use to interrogate this, and we're going to look at how to do that with this tool. But just kind of, get excited about this. This is maybe some use cases for this sort of approach. On the left here, we have a NASA paper which shows how they use it to do flight simulations for the Ares 1 rocket, which never actually flew. But this is actually my background, not that rocket program, but doing flight controls on launch vehicles. So, I can say with certainty that this is a major reason that when we launch to Mars, it actually goes up reliably and robustly. Kind of in the more popular sphere, Nate Silver at 538 has used these sort of techniques to do election forecasting. And how accurate that's been is a little bit up for debate, but I'm pretty confident that he's done better than everyone else in that space for the last several. And on the business side, I don't know how many people here interact with that side of the house, but if you assign uncertainties to budget predictions or task durations, you can start to get a sense of the total range of how much your project might cost and how long it's going to take. And that sort of information is very valuable. But the broader point here I'm trying to make is this technique is domain agnostic. It's kind of broadly useful. But it also follows the same sort of workflow. So we're going to look at that. So the general workflow for doing this is you start off in your middle here with your computational model. And hopefully you have that already. If you don't, your first step is to build that. To sandwich that, we're going to feed it kind of randomized inputs. And each of those set of inputs for each case is going to give us an output. And we take those randomized outputs and do work with them. Instead of point estimates, our inputs are going to be drawn from input distributions. And we'll talk about how to kind of select these distributions in a little bit. At the other side, we're going to conduct our analyses. And this part of the whole workflow is kind of officially termed forward uncertainty propagation. And that's the core problem that the library I wrote here tries to solve and make easy. Part of the loop here that we're not showing is closing the loop, model and parameter validation, which is super important, kind of out of scope for this library, and I'll talk a little bit about that at the end as well. So first off, let's define our inputs. Doing this is pretty easy. We're at the SciPy conference, and the SciPy stats module has a bunch of these already defined. So what we're going to do is we're just going to pass in the handle to a distribution and the keyword arguments that it expects. The harder problem here might be saying, okay, what range should I have? And, that's going to be up to you. Ideally, it comes from observed or experimental data, or depending on the domain, it could be physical limits. Maybe a supplier gives you a spec sheet, and you blindly trust them to hold to those numbers. In the worst case, you have a domain expert give their best guess. And they just have to be careful to make sure that guess is pretty conservative. So once we have those input distributions defined, that gets defined as an input variable, which kind of is what these rows are at the top of the graph here, just showing kind of the broad structure of how Monaco is set up. You have an input variable, and for each case, that's split into a bunch of values, each of those random draws. And then all of the values, for each case gets packaged in one of these case objects. One case runs one instance of your model, and then it spits out output values. Those values from all the cases get packaged into output variables, and then you can do work on the output and input variables and post-process them and analyze them. But we need to make a little bit of glue to stick this structure around your model. So there's three kind of functions that each user needs to define. The first is the run function. This function either wraps or just directly implements your model in Python. To that, we need to have that interact with each case. So on top, we have our preprocess function, which grabs input values from each case and structures it into a format that your model expects, passes it on. And on the other side, we have a postprocess function that grabs all the raw outputs and extracts output values for each case. And in the live demo, I'll kind of step through how this works. Oop. At the end, you need to analyze results. One of the major things you want to do here is just plotting, and so there's no real substitute for just looking at plots. You really don't want to rely on summary statistics all the time. So Monaco.plot will take in one or more variables and automatically choose kind of the best plot type to show based off of the collection of variables it is. You can calculate statistics, excuse me. So you can say, from these results, we want to figure out the mean, the percentiles, variance, whatever statistic you want. And then since we have a bunch of data, we can bootstrap that to a specified confidence level. Sensitivity indices are a useful tool. They're essentially a ranking of your input variables and how important they are to an output variable variance. And when you use the right methods, it's not just the first order effects, but it includes all the nonlinear interactions as well. So how do we do this? Let's go to the first live demo. And for the first demo, let's zoom in here. Is that big enough? For the first demo, we're just going to roll 2 pairs of dice and add them up and see what the sum is. So the steps that we need to follow here are write those user-defined functions, which we just talked about. Initialize the sim object, define our input distributions, run it, and then analyze the results. So we start off with our input ports. So we import Monaco, and MC is the shorthand I've been using. And we also need to import the statistical distribution we're going to be using to model the outcome of the dice roll. Next is our 3 user-defined functions. So again, the run function is just, it either wraps our model or just directly implements it. And ours is really simple, so we're just going to directly implement it. We take in 2 numbers from each of the dice, and we add them together, and we return the sum. The glue around that is, again, interacting with the case object. So our preprocess function takes in the case, extracts the value for each input variable, and we'll define these names in a second, and returns both of these. And then on the other side of run, our postprocess function, again, takes in the case, the outputs from our run function, and just adds that output as an output value for the case. And then that value for all the cases will get collected back up into a variable. And then we structure it in a dict with these special keys, and those are good to go. We then kind of initialize the sim object. So we declare MC sim, give it a name, give it a number of random draws to perform. Right now this is pretty arbitrary. We pass it this dictionary of our user functions, and then we pass it a seed, which is optional but highly recommended for repeatability of results. This seed will propagate throughout the simulation. Now we add our input variables. So we give it a name, we pass it the handle of that statistical distribution and the keyword arguments for that distribution. And randint with these keyword arguments is just give us 1, 2, 3, 4, 5, or 6 for a 6-sided die. And we'll do that for die 1 and die 2, and we just need to make sure that those names line up with the variables we implemented up here. And then don't blink, because this will be pretty fast, but we run the sim. And when you're just adding 2 numbers together, the computer can go pretty speedy. But at this point, we want to look at the results. So let's plot it up. So we, up here, remember we added an output value, gave the name of sum, so that's become an output variable. And so we can plot that variable. And if you're familiar with kind of the odds of what number you're supposed to get when you roll 2 dice, this is exactly what it should look like. Let's do some statistics on it. So to that variable, let's add, calculate the mean, let's calculate the percentile, and we'll make that the 5th to 95th percentile range, and we'll just plot it again. And we see that, hey, the mean is 7, 95th percentile, 5th to 95th percentile range is like 3 to 11, and we understand what these dice are going to do. This is a pretty basic example, so I have a more exciting example that I'm going to run through quickly. I wanted to do rocket flight because, again, that's my background, but one, since I've done that professionally, there's laws against me showing that, and two, the RocketPie guys I think are going to do it better in their talk tomorrow, so go check that out. But instead, we're going to look at baseball, which is actually a pretty similar problem. What we're going to do is we're going to assume the baseball has just been hit by the batter and is flying through the air, at some speed, some vertical angle, some side angle, and then it's going to be acted on by gravity and air resistance, and let's see where it hits the ground. So I'm going to gloss over kind of the actual model here. Suffice to say, it's just physics of flight. But it follows the same structure. So we have a run function, which is doing all of the math. We have our preprocess function, which is taking all of the input variables, pulling their values, and passing it on to that case. You notice here that we have a mix of randomized variables and also constant ones. So we're assuming a constant mass and diameter here, and we could add those as variables that take on variation as well. That's up to you. And then on our postprocess function, we take in the case object, and then kind of the time, position, velocity, acceleration of the ball, and we're doing some post-processing on it. So we can say, oh, our speed is the root sum squared of each of the velocity components. Or we can say, when we land, are we outside the outfield? Like, did we hit a home run? And we package those again into this dictionary with these keys. We define our sim. We defined our input variables. Here, I'm using a mix of uniform and normal distributions, and these numbers were chosen to make the results look pretty and not to accurately represent the game of baseball. But we can now run our sim, and it's a little bit slower this time because we're integrating over time. But it's done, and now we can examine it. So I'm just going to run through some plots here, kind of show what library can do. So let's look at the trajectories over time, and we're going to highlight the home runs. So it's just a matplotlib plot. It's taken in all of our trajectories, and it's showing kind of how the whole ensemble of results look. And these are called spaghetti plots for obvious reasons. Maybe we want to look at just one variable, so maybe let's look at the height. And we'll calculate the mean and the 25th to 75th percentile just for fun. So this is kind of a 2D spaghetti plot. You can see maybe the mean and the percentile range wasn't the best choice here because a lot of the data drops out early, and so every time you lose a data point, the plot jumps. But it gives you a sense of what you can do with this. In terms of kind of getting a relationship between the inputs and outputs, this sim.plot will do that. And I'll zoom out for a second here. And what it's showing is kind of the relationship between each of the input variables and each of the output variables, and a scatter plot between them. And when you look at this, you should really spend a lot of time looking at stuff like this and understanding the behavior of your model to each of the inputs and outputs. In this case, maybe I care about landing distance, and I say, oh, the launch angle, which is kind of cut off here, but the launch angle seems to have a pretty strong relationship there. Maybe we just plot that one. So we plot our launch angle versus our landing distance, and we can really start to dig into the data here. And I mentioned sensitivity indices before. This is what that looks like. And again, this is just a ranking of what inputs are important to the outputs. And we see launch angle is most important by far, and then speed, wind direction, and all that plays in as well. All right, I'll zoom through the other features here just in the interest of time, but we can do parallel processing with everyone's favorite library Dask. There's some functions built in to help you determine how many cases you need to run. There's file input-output, so you can save and load the sim and case objects, because sometimes you have a really expensive model to run and you don't have to want to run it every time you need to relook at the results. Alternatively, you can import or export the variables to JSON or CSV and trade out any part of this workflow with external tooling. Also, you don't just have to do random sampling. You can use quasi-Monte Carlo sampling, and I believe there's a talk on that as well tomorrow, which should also be good. I glossed over this part of the workflow, the model and parameter validation. It's a really important thing to do, but it's also a genuinely hard problem. To rigorously do this, you need a lot of test data, and you really shouldn't be using this tool. You should be moving to a full probabilistic programming language. And that's a pretty high barrier to entry. So a more typical treatment that I've seen is more like a subject matter expert, kind of validating model behavior, really digging in and poking at it, anchoring the input parameters well and making sure they're defined conservatively. And a tool like this can actually help in that process because those corners of the input space where we found monsters are also where you can find corner cases. And in the end, you might end up with a small family of test data. You compare that against your expected results here. There's ways to formalize it, but really you're just trying to make sure that it lands up in the meat of your expected probability distribution. But it's generally outside of Monaco scope. There's other tools out there that can help you with that. So this is kind of a view of what I think are the best ones in the ecosystem right now. On the basic side, I highly recommend playing around with Guesstimate. It's just a web tool, and some guy here has made a Monte Carlo simulation for how long it's going to take his toddler to get ready for preschool. So that's fun to play around with. Monaco, I think, does a good job of doing everything pretty well in a single shot. But if you want more fine-grained control, then I think UQPy is kind of the next step after that. And then if you really want to close the loop, again, you're going to need to move to a probabilistic programming language. And Stan and PyMC are really the biggest players in that space. This is just a bunch of random stuff that you can screenshot on YouTube. I think the one thing to draw out here is that this is alpha level software. This was a passion project for me, and it's a pretty good alpha. It's pretty well unit tested and exercised, but API might change, so play around with it. And I believe that's it. Questions?
Thank you for your talk. That was super interesting. We have quite a few questions in the Slack.
Awesome.
So some of them you kind of addressed, but I'm going to re-ask them just maybe for a little bit of clarification. If the speaker is familiar with Dakota, how does Monaco compare with it?
I'm not familiar with Dakota.
Okay. Well, we'll just move on from that then.
Okay.
That's fine. So the next one is, how does your package compare to OpenTurn's UQ Lab, which you mentioned in the in your like second to last slide, or even Batman?
So the other two I'm also not familiar with. So UQPy has a lot more bells and whistles and a lot more things you can trade out, and how you do your sampling, how different pieces interact. I wrote this to be the tool I wanted at previous companies. So it's designed to have same defaults and kind of a single workflow.
Nice. Yeah, I really liked like how smooth it was to kind of work between setting up your problem and running it. It was really nice. So another question we had is, can you incorporate surrogate approximations for expensive, high-fidelity computations?
Surrogate approximations.
Sam Friedman, maybe you want to like reply to clarify, so because I don't want to like.
I will say all the output data is you can access it through the objects. So if you want to post-process in other ways, easy to do.
Okay.
One thing that he might be getting at here, I'm not sure or not. There are other sampling methods that use feedback. So Markov chain Monte Carlo kind of follows gradient descent and kind of optimizing for a specific output. That's definitely a more efficient approach if you know what you're looking for at the end of it. Personally, I've found a lot of the value in this to be exploratory and kind of getting at every corner of the input space, not just the ones that you think are important, or not the ones that are important to what you think you want your output variables to be tracking.
Okay, thank you. So then another question is, can it handle dependency between parameters, e.g. using popular modeling?
So right now, it can't do correlated inputs. You could kind of do one step removed, like have correlation as a random parameter, and then process it looking at the output. That's work forward. I've got a roadmap. That's on it.
Yeah, it was really cool to see that you had a roadmap, even as an alpha stage project. I was kind of curious, do you have a lot, like, what does your user base look like, and are you kind of implementing features that you're interested, or?
The user base right now is just me.
Okay, so you are incorporating user feedback, but just yours?
Right, yeah.
Yeah, okay.
I think eventually I'll lobby to use this professionally.
Yeah. Okay, cool.
Yeah.
Do you, so is there, like, other than what you kind of listed on your roadmap on your second to last slide, are there like any particular big wishes that you'd like, or maybe if there's a potential contributor in the audience, something that you might like to see?
Sure, anything that helps. Again, I've got a roadmap on the GitHub page. Yeah, I would say apply it to a problem you're having, and then if you see something that it can address, that's where you want to dig in.
Okay. And then I think the last question we probably have time for is, how are you choosing which features and algorithms to implement moving forward?
I just think about kind of stuff I'm looking to figure out. Mm-hmm. Also just reading literature and saying, oh, this is the newest, latest, and greatest practices for this sort of approach.
Okay.
Saying, okay, this is how we should do it then.
Okay, well, let's thank our speaker again.